in this last lecture, what I'm going to do is to describe a model of a polymer that lives in disorder, but this time the disorder lives in all of space. So contrary to what we saw in lectures 4 and 5, where the disorder was either living along a linear interface or living along the polymer chain itself, there is now disorder all over space. And the polymer chain is interacting with this disorder. And we will again see that there is a phase transition. And the phase transition will be of the following type. If the disorder is weak, so if the interaction that the polymer has with the disorder is weak, then it will largely ignore the disorder and it will start to do a behavior that is just like that of a typical path, and that would be diffusive. Whereas if the interaction with the disorder is strong, then what the polymer will try to do is to hunt for the special spots in this spatial field of disorder where the disorder is very high, and it's going to have a very different behavior, namely it's going to hunt for good spots, and we will see that in that case, in fact, the polymer will have a super diffusive behavior. It will start to run around very quickly to find good spots if the reward to find those good spots is good enough. And this model was already briefly mentioned in the Monday evening talk that Dima Joffe gave. And so he mentioned this problem. At the end, I will come back and make a few remarks about an undirected version of this problem. And what we will see that will be the main technique to deal with this problem is martingales. So there's a particular martingale coming up, and that will be a key in the understanding of this model. Okay, so I'm going to set up the definition of the model. I need 3 ingredients for that. And the first is, as always, a set of paths. So in our case here, Wn will be the set of all n-step directed paths. We make the word directed here because that will put us into much better shape to discuss the problem, and with only up and down increments. It's possible to generalize this, but we will not do this, at least not in this talk. And then there will be disorder, and this disorder will be a space-time disorder. So in fact, this is not now going to be a sequence, but it's going to be a whole field where I runs over time and x runs over zd. And these are ID R-valued random variables, of which we assume that their moment generating function is supposed to be finite for all real beta. So we want sub-exponential tails. Okay, so this is the disorder that comes in the system, and it's different from before because here the disorder lives in time and space. So this is a d plus 1, or rather a 1 plus d dimensional model. Let's say 1 plus d dimensional model. And when I wrote this here, I mean that the increments are sort of, let's say, with nearest neighbor increments. And if you do this in 1 plus 1 dimension, it means up and down. Okay, so that is the second ingredient, and then we have to define our Hamiltonian, and the Hamiltonian will depend on the parameter beta and omega, and if you take a path in this set, it will simply be minus beta times the sum over all times of omega I w I. So basically, this sums the disorder along the space-time path. Okay, and beta is a parameter that we will want to take non-negative, and this is the strength of the disorder. So it's an overall factor that gives the strength. Okay, and then once we have these three ingredients, then we get our Gibbs measure as always. It's an exponential tilting according to the Hamiltonian that depends on the disorder of a path measure that has no interaction, and for this Pn we simply take the law of simple random walk on ZD, so the Pn plays as always the role of what you would get if there was no interaction with the disorder. Okay, so this defines the model. One dimension in time, d dimension in space. Take all nearest neighbor directed paths, sum the disorder along your path. If you would set beta equal to infinity, or rather think about beta being very, very large, then what this Gibbs measure does is that it will simply single out the paths that follow a trajectory in your time plus space field where the sum of the disorder is the largest possible. Okay, so of all possible paths, it would pick the one with an overwhelming probability where the sum is largest. And this corresponds to oriented first passage percolation. So in the limit as beta tends to infinity, the path behavior of this model maps onto oriented first passage percolation, where you assign weights to the various sites and you try to find the path that maximizes the sum of these weights. And this was already briefly mentioned in the course on noise sensitivity that Christophe Garbin and Jeff Stife spoke about in the first 2 weeks of the school. In our case, we're going to have beta anywhere between 0 and infinity, and so what we have is a kind of softened up version of oriented first passage percolation. The path will want to follow trajectories along which it can make the sum of the disorder along the path large, but it doesn't have to look for the largest sum because beta doesn't give you an infinite reward for that. So that's why this model is sometimes referred to as oriented first passage percolation at positive temperature. The model also has another name called directed polymer in random environment, but I don't think that name is any more distinctive in this course, at least, because what we've been doing in lectures 4 and 5 was also directed polymers in random environment. So there are different ways of calling this. Actually, this model arose originally in a completely different context that was not polymers. It came up when people tried to describe interfaces in disordered easing models, and they use this model as a kind of toy model to describe that. So the model actually arose in the physics literature, and since then it's been very intensively studied. Now, because the disorder is everywhere, this is not a model that we can solve explicitly, even in one dimension. It's not, so I mean 1 plus 1 dimension. It's not an easy model, yet we are able to say a number of interesting things about it, and that is what I'm going to tell you about. And the key tool in understanding this model is the following. We take the finite end partition sum at a fixed realization of the disorder, and we divide it by the mean of the partition sum over the disorder. So this is the quotient of the quenched and the annealed partition sum. And this object for fixed beta and omega is a random sequence. It's random because of the omega. So this partition sum is an expectation, as we know, of overall paths of e to the minus Hamiltonian. And this is a random sequence of numbers. And this is a martingale with respect to the national filtration that you get from your disorder. So you look up to your disorder, you look at your disorder up to time n, and then this object with respect to that increasing sequence of sigma fields becomes a martingale. And that is very easy to see. The moment we realize that we're going to write this out as a product, so this z, z has an e to the sum in the exponent, so I can write this out as a product. So from this part here, I get this numerator here, because that is the sum over these things is what was minus the Hamiltonian, that appears in the Gibbs measure that for which this is the normalizing constant. And I can normalize it because this one has an easy expectation. This you can compute is just m beta to the power n, where m beta is the moment generating function of the disorder. And so this object here is the expectation over all paths, where now S is a random draw from my set of directed paths according to this reference measure, which is this law on path space when there is no interaction. And if I condition on this object here at time n minus 1, then that just splits off the product up to n minus 1, and the term with I is equal to n remains. If I've conditioned on the y n minus 1, it comes in front of the expectation, and what you are left with is the expectation, only having to take the expectation over the disorder at the last point, and that is just 1, because the definition of m beta is exactly the moment generating function. So if I take the expectation over this thing conditioned on the thing at n minus 1, I just get the thing at time n minus 1, and that is the martingale property. So it is easy to check that this is indeed a martingale. It's a martingale that starts at 1. Its mean is fixed at 1, and because it's something that talks about exponentials, it's also a non-negative martingale. This thing is positive for every n, and it's positive with probability 1. I would need to assume that the disorder is non-degenerate. So this has a law that is non-degenerate. Okay, so this is a key object, and it's giving us, if we understand what this thing is doing, we have information about the quotient of the quenched and the annealed rate function. And if that quotient is doing something interesting, then we will be able to say whether the quenched and the annealed partition sum are comparable or not comparable, and that is going to give us information about the effect of the disorder on the whole problem. So being able to understand that will give us an entrance into understanding this problem. So, well, here is what is our first observation, knowing that there is this martingale around. By the martingale convergence theorem, it's a non-negative martingale with mean fixed at 1. By the martingale convergence theorem, this, if I let n go to infinity, this will have an almost sure limit. This limit will exist. And now there are two possibilities. This limit, well, this limit will typically be random. It will not be a constant. But it could be that this limit is strictly positive with probability 1 or 0 with probability 1. It cannot be a mix of the two, and that is because whether or not this thing is positive or not only depends on the tail of omega, because remember that this is a product of terms, and so whether this product of terms is going to go to 0 or not will only depend on the tail. And the tail of omega, because omega is an ID field of random variables, this tail is trivial, and therefore the event that this goes to 0 will have probability 1 or 0. So we are in a situation where either with probability 1 this limit is positive, where this p is the law of the disorder. This martingale is random only because of the disorder. The expectation over the paths have already been taken. Or it could be that this limit is 0 with probability 1. Now, so there is this dichotomy. We do not know when this dichotomy is occurring, so for what values of beta at present and for what choices of the law of the disorder, we do not yet know, but we do know that these are the only two possibilities. And these two possibilities are referred to as weak disorder and strong disorder. So if you wish, they are the definition of what we would call weak disorder and strong disorder. And at this point, it's not yet clear why we would attribute these names to these two phases, but it's not so hard to imagine that this is a good name, and we will come to appreciate that it really is a good name, simply because if this is happening, that this stays bounded away from 0, remember that this is the quotient of the quenched and the annealed rate function. So if this thing does stay away from 0, it tells us that the annealed and the quenched rate function are comparable, even asymptotically. And that must somehow mean that the disorder isn't doing so much. And so it would be, that's why we would say that ought to be, that deserves a name that is weak disorder. Whereas if this tends to 0, then it would mean that the quenched partition sum in the limit as n goes to infinity is going to be really much smaller than the annealed partition sum, and therefore somehow the disorder is doing something significant. And so already from that very qualitative observation, we could say it is not a bad idea to give these two phases these names. And we will come to appreciate in a second why that is okay. Okay, so what I'm going to do in the remainder of the lecture is to say, well, we're going to look at these two phases. We're going to find conditions on the parameters in our problem under which we fall into these two cases. We will not be able to fully classify them, but we will be able to come a long way. And we will see, and this will be formulated, what's written here will be formulated in theorems on later slides, is that when you're in the weak disorder case, so the case where the quenched and the annealed rate functions stay comparable, then the disorder isn't doing so much, and in fact, the typical path will have a kind of diffusive behavior that is hardly going to take notice of the disorder. Whereas in the other case where the quenched and the annealed partition function are really very different, the disorder has a serious effect, and we will see indeed that the path starts to hunt for spots in the space-time disorder where the disorder is strong, and so that it gets a serious reward if it manages to move to these rare spots. And so the path is going to be much more wild here, and it is predicted to even be super diffusive, but we will be able to say a few things about it that will sort of corroborate this picture. And so you have to think of these two phases as, in terms of the path behavior, describing a situation where you're not going to hunt for good spots and where you are going to hunt for good spots. Well, here's the first theorem. The first theorem says these two phases, which we know are mutually exclusive because they correspond to this quotient of partition functions going to, not going to zero and going to zero, they are separated by a unique critical value. So if I make a choice for my disorder distribution, so I'm fixing the law according to which I pick my ID random field. Once I've frozen that, then there will be a unique critical value, and this critical value will depend on the law of the disorder that you choose, at which there is a separation between these two phases. And there will be a unique critical value such that if you are below this critical value, the interaction strength with the field is weak enough so that you will fall in this weak disorder regime defined on the previous slide. And if you're above it, you will fall in the strong disorder regime. We do not know whether the point BC is actually belonging to this one or that one, but definitely there is a unique critical value. And the way this is proved, this was proved in a paper by Komets and Yoshida using this martingale approach. And basically what they did is that they look at some particular quantity of the limit, which happens to be the expectation of the square root of the limit, and they proved that this expectation is monotone in beta, and that therefore, the distinction is this zero with probability 1 or is it positive with probability 1, and because it's monotone, you can only once cross over from one regime to the other. So they found a monotonicity in the problem and accordingly concluded that there is a unique critical point. This critical point can be zero, it can be positive infinite, and it can be infinity. And we will see that all three cases are appearing. So if it's zero, then everything is strong disorder. If it's infinity, everything is weak disorder. But there are cases where it's somewhere in between, and you really have a phase transition. Now, this only makes a statement about there being a regime here where the quenched and the annealed partition sum are asymptotically comparable, and a regime here where the quenched and annealed partition function will not be comparable in the sense that the quenched will be much smaller than the annealed. In terms of the free energy, So I can define a quenched and an annealed free energy. So the quenched free energy would be the exponential growth rate of the numerator in my martingale, and the annealed free energy would be the growth rate of the denominator of my martingale. If these two things are comparable, which they are in the weak disorder regime, then these two growth rates are obviously equal to each other. So everywhere on the interval between 0 and beta critical, not including beta critical, I find that these must be identical because even these things are comparable. And then because free energies are continuous, I can add the critical value here and say it must then also still be true on at the critical value for the free energy. The free energy is a much cruder way of comparing these two partition functions. And it is definitely expected that they will become really strictly different once you go past this critical value. And in one dimension, this was proved by Comets and Vargas. So sorry, there's an S missing here. And now it has essentially been settled completely in papers by Lecoin. There's even a recent paper that I haven't cited here. So we have a situation where, in terms of free energies, there is this kind of behavior. Where you have the annealed free energy as a function of beta and the quenched free energy of beta. So also at the level of the free energy, you really see something happening at this phase transition. Now, what I'm going to do next is to tell you some more detail about what is happening in each of these two phases. And in order to do that, I need some definitions. I'm going to need to define 3 objects for you. The first object is something that only depends on the random walk. And pi d is the collision probability of 2 independent copies of the reference random walk. So in our case, the reference random walk is simple. It's simple random walk. So, but if I would like to generalize this model to more general random walks, that's the definition that I would have to give. So in our case, pi d is 1 in dimension 1 and 2, and it's less than 1 in dimensions greater than or equal to 3. Okay, the second ingredient that I need is an ingredient that only depends on my disorder law. And there are 2 functions, and I'm going to draw a picture of them because it's really only the picture that matters. It's sort of two curves. They are not linear, but let me draw them as just any 2 curves. And they have the property that they coincide at beta is equal to 0, and they will become different. And they are increasing for positive beta, and the delta 1 is lying above the delta 2. So there will be some curves like that. Their precise shape will depend on the law of the disorder, and they are defined in some sort of way. And these quantities are put here because they're going to come up later. So these are simple objects that you can compute, depending only on the walk and on the disorder. And then there is a third quantity that is going to be the following. So it's called max n beta omega. It is the maximal probability over all sides of the endpoint of my path being at site x. So what this thing measures is the maximal probability to be somewhere at time n, right? And there will be a distinction saying if this as n tends to infinity goes to 0, then it means that my endpoint has a spread out distribution because there is not a single site that receives any appreciable probability in the limit of n going to infinity. But if it converges to something positive, then it will be not spread out. So if that happens, then there will be some site, we don't know which side it is, where the polymer has a positive probability to actually be there. So those are two very different situations. Okay. So having these three ingredients, I can tell you about two theorems that give us information on what is happening in these, under certain assumptions. And we're going to have two parameter regimes. There will be a certain parameter regime, so two parameter regimes, which I will call 1 and 2, and I will describe what they are in terms of the parameters of my model. And we will see that the first one will imply behavior of the weak disorder type, and we will see that the second one will describe behavior of the strong disorder type, but the reverse is not true in the sense also that these two things do not cover everything yet, and I will come back to that as we go along. So the first result says, and this comes out of a sequence of papers that was started with Imbrie and Spencer, and Bolthausen had an important simplification of that argument. And there were I'm citing here a whole bunch of papers that were also looking at sort of different points of view on this and further refinements. So this is a story of which this is only the core, but much other stuff has been going on around it. And this theorem says if I take dimension greater than or equal to 3, and if I'm in a situation where the beta and my disorder law is such that this number, which I have defined explicitly, but of which there is some picture there, is below log of 1 over pi d, then we are in a regime where the mean square displacement of the path grows linearly omega almost surely, so this is diffusive behavior, and correspondingly there is a spread out property that for very large n, there is no site that receives any appreciable probability of hosting the endpoint of the path. It perhaps comes as a surprise that this limit is 1 and that it wouldn't be some number, some diffusion constant. The fact that the diffusion constant here is 1 and it is not renormalized, if you wish, by the disorder is because we are talking about directed paths. The annealed model is really trivial. If I just look at the annealed path measure, it's just the simple random walk, the directed simple random walk. And the fact that this is not renormalized is coming from that observation. The second theorem is a regime where you are either in dimension greater than or equal to 3, and you ask the lower curve to be above something that is higher than what we were asking in the other curve, or you are in dimensions 1 and 2, and then it's good enough to have any positive beta. In that particular parameter regime, we know the following. We do not know yet what the path behavior is, but we do know that this particular maximal probability is not tending to 0. So we do know that for large n, there is going to be some site, we don't know where it is, that receives an appreciable probability of having the endpoint of the polymer there. So this is a manifestation of the fact that this polymer in this regime really wants to hunt for the good spots in the disorder. And it is telling us that there is somewhere at least one point where it likes to be with a probability that is larger than 0 and that is bounded away from 0. It's stated here in weak form that there is some sort of subsequence, but at least it says there is not spread out behavior, and therefore in this regime the path definitely is not diffusive. So it's really a manifestation of this large effect of the disorder. So let me draw a picture of this case. So we do know that in this case we have strong disorder for all positive beta. That is what the second theorem says. And in this case, we have weak disorder or strong disorder in two sub-regimes. And so if I would draw a picture of that, I could note that this number here, pi d, is larger than 1 over 2d, because that's the probability that they would collide after one step. So the log of 1 over pi d, so if I put here the log 2d, and I would put here the log 1 over pi d, then these are ordered in this way, yeah. And the first regime was saying, I want this curve. So let me see. So the first regime was saying that I want to find this point here, and I was looking at this regime here, and the other one was I was looking at the lower curve and I wanted to reach this point here, and so that was the other regime that we were looking at. And so you see from this picture that these two regimes do not capture the entire parameter space yet, and I will draw a picture about that in a second. So maybe I just do that right away and swap the order of these two things. So actually, if we call this number here beta critical 1, and we call this number beta critical 2, and they are really different, they do not coincide, then we have found essentially that on the left of one of the regions, on the left of beta 1, you are in the weak disorder regime, and on the right, you will be in the strong disorder regime. So let me draw a picture of that. So we do have a situation where the critical value is somewhere, and we have lower we have a lower bound and an upper bound for this thing in terms of, so here is where things are weak disorder, and here they are strong disorder, and we have now upper and lower bounds on what these critical values are, and they are completely simple to compute because these functions only depend on the disorder law, these only depend on your random walk, and you can find these values explicitly. And there are, it turns out that in, so this theorem is really only interesting for d greater than or equal to 3 because we already know that beta critical is 0 in the case that you have 1 and 2 dimensions. So in 3 dimensions it looks like this, and it actually, if you look at these numbers themselves, there are already several cases. They can both be finite. It could be that this is finite and this is infinite, and it can also be the case that they're both infinite. So if they're both infinite, then you know that beta critical is infinite. So this depends on the choices of disorder and your random walk. So there are simple choices of the disorder and the random walk for which you will find that beta critical is 0, which is 1 and 2 dimensional, and there are cases where you find that it's infinity and you're also done, but there are cases where it is some finite value somewhere in between. Now in this strong disorder regime, where all that we know for the moment is that you have this not spread out property, that we know that in the strong disorder case there will be somewhere, some point that catches an appreciable probability to be the point where the endpoint is. It's predicted that the mean square displacement throughout this phase has its own critical exponent. Again, this is rough in the sense that you should put a little o of 1 in your exponent. And it's believed that this number is always strictly larger than a half. So really saying, well, it is really super diffusive behavior because the path is really hunting for these good spots in the disorder field. And in 1 dimension, there's a conjecture that it's 2/3. This is a very well-known exponent that has deep relations with many other things that are happening for instance, in percolation. I do not have time to go into that. And for 2 dimensions, it is believed to be smaller than 2/3, but still larger than a half. So that, but then this number we haven't been able to really pin down. And there are some partial results in this direction. There are models where you take a very particular choice of the disorder, and then you are able to make progress on this question and really say something more about the path. Here are various papers cited here. So these papers also look at other exponents that give some more information about the roughness of the path. And so there has been a lot going on in that direction, but the last word about this has not yet been said. It's still, even in 1 + 1 dimension, an open problem to prove that the path is super diffusive with exponent 2/3 throughout this entire strong disorder regime. Okay, now I already told you that we have bounds on this critical value. This number is a complicated number. We do not know what it is, but at least we have these 2 bounds. Very simple bounds that basically come from a second moment calculation. Now, what could we do to improve these bounds? What has been going on to try and sharpen these? There have been various attempts to improve on these bounds. And a large part of this was dealing with fractional moment estimates. So the bounds that I wrote down come from second moment estimates. But you can try to try if you can see, with the help of martingale techniques, to control lower moments of your martingale, and therefore improve your control on the critical curve. And there's been a whole, there's a couple of papers trying to do that. To some extent, this is a very canonical way of trying to improve your estimates, but it's also somewhat cumbersome. For instance, if you take this paper, then they find good estimates, but you have to really, at some point, do numerical computations to actually get numbers out, and things tend to be restricted to things where the disorder is of a certain type. So there's very interesting progress in this direction, but it's also a little bit cumbersome, I would say, to go and improve that. What I want to tell you about next is that there was a new idea on how to improve the estimate that was put forward in a paper by Matthias Birkner 5 years ago, in which he said, let's try and take our martingale, and instead of looking at fractional moment estimates, let's see if we could do something with size biasing. Size biasing is a celebrated way of trying to get control on the behavior of your martingale. And in a way, you should think of this as trying to push the fractional moment estimates to the maximum, in the sense that you're going to do a 1 plus epsilon estimate for very small epsilon. That's basically what size biasing is trying to do. And so I want to spend the next 5 slides on telling you what Matthias Birkner did. So he said, I can estimate my critical value in terms of a certain quantity, and that quantity is a somewhat more complicated quantity of my random walk. Remember that the estimates that we had involved, so the upper and lower estimates were both something that involved some functional of the disorder and some very simple functional of your random walk, like this log of 1 over pi d. And Matthias says, well, there is a somewhat more complicated functional of my random walk that if I use that, I can improve on the estimate. And what he said, well, let's define this number. Let's take the generating function of, I take 2 independent copies of my random walk. What is this? How do I close it? Let's see. Well, fish are. Okay, that's what we'll do. Gone. Okay. Let's hope it doesn't reappear. So it says, take 2 independent copies of your reference random walk, which is a simple random walk in this case, and let's look at their collision local time. So it's something that has to do with collisions again, but it's a collision local time rather than a collision probability. So you count how often they meet. And then what you do, you take you take z to that power, and you take the expectation only with respect to the walk S, and you do not take the expectation with respect to the second walk. So I am freezing the second walk, and I'm asking how big can this be? So how well does the first random walk manage to make this big or large? Now, because this second random walk has ID increments, it has a trivial tail. And so whether or not this expectation is finite will be something that has probability under S prime that is either 0 or 1. And in this formula you say, look for the largest z for which this is still finite. If it's finite, it will be finite with probability 1, but look for the largest z, and let's call that z star. So this is some number that involves basically a large deviation property of the intersection local time of two random walks in which I freeze one walk. And then what the theorem says is define a B star critical, which is as very similar as the definition of the beta critical 1, except replace the log of 1 over pi d by this number. And you can prove that, okay, so I will come to that later. And then the theorem says, if beta is below this number, then I will be in the weakly disorder regime. So Matthias proves that there is a number here. This is his beta critical star above, such that below I will be in the weakly disorder regime. And therefore, it must be that the crossover for the weakly disorder regime, which is our true critical value, is on or above this lower bound. So this result improves the lower bound, except that we have yet to see that these two things are not the same. So the question is still, are they different or are they the same? Okay, now before I answer that question, I want to give you an argument in 4 steps of how you prove this result by Birkner, and show you that it is indeed something that comes from size biasing of your Hamiltonian. And we're going to do something interesting. We're going to size bias our disorder along the path of the frozen random walk. So let me abbreviate E of I of x as the pieces that you saw. So these are sort of a different way of writing your disorder. Such expressions came up in my martingale, and so let's give this a separate name. So e to the beta, the disorder at time point I and space point x, normalized by the mean of the exponential. So this is an ID field of random variables that, of space-time, time-space random variables that all have mean 1 and that are non-negative. So I want to talk rather in the E language than in the omega language. And what we're going to do is I'm going to introduce a sized bias version of this whole field, which I get by simply saying the law that I get for this new field, which is will again be a time-space ID random field, but it will have this, not the law, same law, marginal law as these things, but I will size bias them, saying the bigger you are, I will reward you by giving you more probability for that. So the probability that this size bias random field takes a certain value is something that is the probability of the old field doing that, but multiplied by the value of the old field itself. And so this is a way of saying I am going to tilt my probability distribution of E in a way that is linear with the outcome. Okay, so if you are given a certain law of the marginal of these, which comes from the law of this, then you can compute the law of the tilted random variables. And I do not need to normalize this because the e's already have mean 1. So imagine that I have this field, ID times space field of the original disorder, but written in the E language, and I'm going to get a tilted version of that where every side I simply tilt it according to its value. So it's a somewhat thicker field. Then what I'm going to do is I'm going to use the original field and the tilted field, which are two independent copies, this one being a thickened up version of that. And I'm going to read either this one or that one, depending on whether at time I, at position x, my path S prime is or is not there. So I say, if my path is not at site x at time I, then use the old disorder. If, however, it is at a site x at time I, then use the tilted disorder. So this now is, for a fixed path S prime, an independent field of random variables that looks like the old field outside the path, but looks like the biased field on this path. So I am biasing the field along a particular path S prime. And then what I'm going to do is I'm going to use these random variables to define a new martingale, just as I did before in the old martingale where I had really written here beta omega, and I'm now using this E. So the beta is wiped under the rug, and the disorder omega now is written in an E language. So our original martingale was a product along the S path, not the S prime path, of the original disorder. And I now define for every path S prime a similar product of this field that is tilted along a path S prime. So this depends on the original disorder, on the tilted disorder, which come in here, and on the path S prime. But other than that, this is still a martingale. So I'm having my old martingale, and I have a sized bias martingale that is thicker along a particular path S prime. And then the clue of the whole story turns out to be that expectations of certain quantities involving these two martingales can be related to each other. The construction is such that if you give me any function from 0 infinity to the real line, doesn't matter what it is, well, I want to make it bounded so as to be sure that things are not blowing up. Then if I take the old martingale in the F, and I weigh it with the value of the martingale itself, then that is the same as if I just put the biased martingale in my F and then average over everything that is random in that object. So here is the F alone, and here comes the F with a linear factor. And so this formula says, and I will try to lead you through this computation, why this is true for every F that is not too terrible. And this gives you a relation between expectations of these two martingales. And in step 4, we will see that that relation is the clue to finishing the problem, finishing the proof. Now here, let's go through that. It's a somewhat longer calculation, but I'd like to show you bits and pieces of this. So this is the expectation that we want. This object, I first write it as an expectation with respect to the S path, and also with and inside the F. And in front here, I write it as an expectation with respect to an S prime path. Well, S and S prime have the same distribution, so that's okay. Now I'm going to interchange these two expectations. So this part stays the same. And this expectation I bring in front of the other. It is still acting on the product of these two terms. And now I'm going to use the definition of the E hat thing, because the E hat thing said, if I am at a site of S prime, then I will give you a tilting. So everywhere along this path, I see these factors coming up along the path S prime. And so these factors were exactly what I was sticking in through the tilting along the path S prime. So all these factors are exactly taken care of in terms of this new, these new tilted random variables along this path S prime. The expectation of S prime is in front, and then once I'm here, I can put everything together and say, oh, but what was in here was the definition of my biased martingale. Okay, so you have to sit down. This is not difficult, but you can check this argument quietly on your own, and it's not really hard, but you have to sort of stare at this for a while to see why it happens. And then we can now finish the proof. So the claim is, from that identity, the following observation occurs. If the old martingale is uniform integrable, then the new martingale is tight, and the other way around. And that, so let's go back to this equation here. So if this is tight, then it means that this is bounded uniformly above in n, and if that for every sort of bounded f, and then therefore that must mean that the mean is sort of bounded, and it means that this martingale must be uniformly integrable, and the other way around. So out of that identity comes a statement that relates uniform integrability of the old martingale to the tightness of the new martingale. I mean, this is a standard kind of way of doing size biasing. What is important here is that we do the size biasing in a clever way along a certain frozen random walk path. Now, the expectation of the new martingale is something that we can compute. If you put in this, remember this was a product of terms which were looking at E off the path S prime and looking at E hat, which was the size bias version of E along the path. If you do that computation, then you will see that what you get is that this expectation is exactly, you get two walks at points where they intersect, and you get one walk, you get two separated walks at where they do not intersect, and therefore this expectation is just z to the intersection, sorry, the collision local time of my two paths, where this z is a particular number, which is the ratio of the moment generating functions, the 2 beta and beta. So this corresponds to two walks being at the same site and seeing 2 delta, 2 beta, and this means the walks being at two different sites and therefore seeing the square of n beta. And so this becomes the object that we had introduced this collision local time. And so what we see is that if we manage this to, so if this is finite, so which was the region of, so it's finite for z below z star, then if this is finite, then definitely it means that, so if this is finite, then this definitely is a tight sequence. But if it's a tight, so this is enough to have a tight sequence. But if it's tight sequence, then this is uniformly integrable. And since this is a martingale, that if it's uniformly integrable, it cannot send any of its mass to 0. And therefore, we must be in the weakly disorder regime. Right, so here's the statement again. If you look at the collision local time of two random walks averaging over the first walk but not averaging over the second, so it's a kind of quenched expectation with respect to one of the two walks, then if you find where this blows up, then that will give you the critical, that will give you lower bound on the critical value, because if you're below here, the Z will be below Z star and you will be in the weakly disorder regime. So, indeed, this then gives the picture that I was drawing here, except that we still have to worry about the fact that the Z star is really different from the pi d that was giving us the same formula for beta critical 1 for the other lower bound. And so there is a question, is there indeed a separation between these two numbers? Okay, you can very easily, you immediately see that Z star is at least as large as pi d, because if the collision probability is, if you stick in the collision probability in the Z, then this exponential moment is, if you pick any value smaller than pi d, this exponential moment will be finite. And okay, so using this large deviation principle that I was telling you about, of a renewal process, cutting words out of a random sequence of letters, using that LDP, but in this particular context, we were able to prove, and this is one of the applications of that large deviation theorem, we were able to prove that at least in dimension greater than or equal to 5, there is a gap indeed between these two values, so that we do indeed get a better lower bound. And this is a bit like in the pinning model. This frozen random walk and all its increments is what I read as a sequence of letters, the letters taking values in the d-dimensional lattice. So the jumps of the walk I want to read as a random word, and then for the collision local time, the other path is just trying to hit the frozen random walk, and in doing so, it's cutting out words from this frozen random walk. So in that language, we are able to use that LDP to describe this behavior. And we had trouble dealing with dimensions 3 and 4. There's not going to be any doubt, really, that these should be separated also in 3 and 4, that is, they are always separated. And this conjecture was recently settled in a number of papers, which I'm citing here, first 4 and in 3, but they still need some sort of conditions on the disorder law, whereas one definitely expects that irrespective of the disorder law that you would pick, these two things are all different. But there's interesting and important progress also in these lower dimensions, so it looks like the prediction is really that there is a gap always, and that really the bound by Matthias is an improvement over the earlier work. So I'm coming to my conclusion. There are some hard problems still on the road. In the strong disorder phase, you would really like to prove that the whole path is going to live in some very favorable, or perhaps most favorable corridor that depends on the disorder, and that it's going to hunt its way through disorder in a particular way that will depend on the outcome of the disorder, but that you hope to describe. So this is in the spirit of the things that Wolfgang Koenig was talking about yesterday for the parabolic answer model, where you also say the solution lives on a certain set of islands that are optimal and moves through space-time to hunt for these islands. And so in this polymer model, you would like to deal with that. And at the moment, we cannot. Vincent Vargas has made a lot of progress on this for situations where the disorder has very fat tails, but this is still largely open. Thinking of this whole LDP technology, of which I've only been able to tell you a little bit, and Francesco Caravana the day before yesterday told you more, one might even try and hunt for a variational expression for this critical value. That looks like a very big challenge, and honestly, I'm not even sure whether I should expect that we will be successful on this on any short notice. And finally, it would be a challenge to remove the directedness and to go to undirected models. And Dima has told us on Monday about work in that direction, but it is hard to describe the path behavior as such. If you make it undirected, it's going to be harder. But if you look at a model where you're going to pull on the polymer and pull it a lot so that it actually even becomes ballistic, then there is a lot of interesting things that can be said. And I already, when I spoke about this on Tuesday about the collapse model is an annealed version of an undirected version of this model. I already made propaganda for this paper and say, go and look at this. It's in the Brazilian Journal of Probability Statistics. It's a wonderful thing. Sorry for making that propaganda for you, but I really believe that. It's a big step forward. Okay, I'm about to wrap things up, and then after I've wrapped up, then I will still want to say something. I hope that this course has shown to you that random polymers are an exciting subject, and that there's a lot going on, and that there are quite a bit of serious challenges. Gord was saying, well, it's nice that there's so many young people, and we hope that they will go on and solving some of these problems. Well, I think here's an area where you can put your teeth into that, and you will have a lot to deal with. And it's an area in which things are coming from various directions. I've been really only talking about the mathematics, occasionally giving you a bit of physics and chemistry applications behind it. And this is, of course, the area where polymers are going to be of absolute major importance and will be studied over the years. And of course, in the end, DNA is perhaps the most important polymer of all. And this DNA molecule can be subject to all sorts of things, and the things that we've been discussing, like collapsing in a hostile solvent, pinning of strands in a denaturation transition, this thing sort of staying close to an interface or trying to pull the strands apart with a force. These are all things that DNA is sometimes subjected to or subjects itself to, and some of these aspects has to have been described. And so there definitely is still a lot out there for all of us to discover. Thank you. Okay, so let me add with a few remarks. I'm going to add to what Gord said about how absolutely wonderful this whole summer school has been. This has not just been a good summer school, this has been a phenomenally good summer school that I think will long be remembered. And of course, another way of describing the role of Vladas is that Vladas is basically SLE 8. He is space-time filling, he's everywhere, and that we have all experienced. So let me say thank you for that. And let me tell you that I really have only one question that is on my mind. What is going to happen to this wonderful blackboard? Because this is another of these things that, you know, is just a singularity. So can I make a small suggestion? There's a beautiful museum of modern art just outside Rio, made by the famous Oscar Niemeyer architect. So maybe we can hang it up there, just the right spot, and on the corner we could put some chalk, a half-eaten sandwich, maybe a pair of glasses, maybe a glass of caipirinha, and just one little minimalistic sign, Clay, EBP, Buzios, 2010. That would be a great tribute. Thank you.
I just want to make a couple of remarks. It was absolutely wonderful for the Clay Institute to be able to collaborate.
Yeah, sorry, you need to take this.
It was wonderful for us to be able to collaborate with the Brazilian School on Probability this year, and it just made this fantastic culmination to the Clay School. So first of all, we're just incredibly grateful for this opportunity to be down here in Buzios in Brazil and see all this and help facilitate it in our small way. The Clay Institute, as I mentioned before, depends a lot on the generosity of others, and I also know that the IMPA will be sending an email out to you all to ask if you've started any research papers or had any ideas which eventually lead to publications. All this school was funded by research institutes or research programs or research grants, so research is a very important part of making events like this happen. So please reply to those emails vigorously with anything that you have and that comes out of the school. I also want to say, I always try to think of something to say to kind of round things off, something a little bit different. And so I was thinking you've been so charged with so many ideas and so much incredible material these last 4 weeks. Sometimes I meet students later and they say to me, I was so energized at the end of the school even though I felt so exhausted after such a long program. So, and the question is, how do you proceed having somehow been exposed to so much material? Well, it reminds me of a little story that I read when I was a teenager. I don't know if any of you remember the book by Michael Ende, The Never-Ending Story. Well, there's a scene in the book where you have this lion who befriends the sort of main character, this little boy. And the little boy's wearing around his neck a little medallion that says, "Do what you wish." So the lion asks him, "Do you know what that means?" And he says, "Well, I suppose it means I should just do what I want all the time, right?" He says, no, doing what you want is the most difficult thing in the world, right? The advice that you're getting on this medallion is to do what you wish. So he says, well, how's it different? Well, the thing is, every wish in some way leads to another wish, puts you in a different place. And that wish in turn leads to another wish. And it's those chain of wishes that eventually lead you to what you really want and what you really want to do. And I think that's kind of how research actually really proceeds. And so if I have a final wish that I'd like to bestow on you all, it's that the wish that was fulfilled, that was started a few years ago between Wendelin, Chuck, and Vladas, this has now been fulfilled in this school. And I hope it will lead you onto many more exciting ideas and wishes that you in turn fulfill in your own research and help you in your future career. So with that being said, I'd like to hand over to Vladas, who's really been the hero. He's made this school the main focus of his life, not just for these last 4 weeks, but he's really been working on this for a very long time in order to make all this happen. So please join me in welcoming him to say the final goodbye and show your appreciation.
Okay. So thank you very much, and okay, we're done. I would like to thank, first of all, Czech. Actually, this idea, we were sitting in Park City, and I think spontaneously came to us, and then we quickly wrapped it in, talked to Wendelin, and in fact, several other towns. Spencer was there very close. So several people were really pivotal, and but many projects since maybe 15 years, mathematical and also organizational, wouldn't come through if not Czech. So Czech was great companion through big part of my scientific career. So I would like to thank you so much. I would like to thank Frank, Gordon, and everyone. Probably most of them are left. So you had this privilege to see key probability figures of contemporary probability, and it has been really pleasure to talk to them during preparation of the school organizing. So actually we had great time in cooperation. There were no difficult moments at any point, and it may sound to you as not completely difficult task, because each of them are kind of working in this area. They're experts. They gave a lot of courses before and will give after. But I think this particular school was really excellent in preparation. I saw how much effort Frank, Gordon, and other people really put it into preparation. So school actually started to be really materialized more than a year ago when we started to speak about courses and TAs. So it was really pleasure to work with you. So, and of course, success of school, I did some little job just putting buses on time, but these gentlemen are really the ones who made it to be such a success. So thank you all. That's it. So there is lunch, and try not to be late for buses, because some people are going to the airport, and I need to talk to you, and Remco, Frank, 1:30. Well, it's not sharp, but let's try to make it sharp.